Hello everyone, hope you guys are doing good. Today we're going to resume our discussion on system representation. We will try to complete the discussion, so let's start. Obviously, whenever we start a new topic, we justify why we are opting for that and how we are going to do that. So that was what we discussed last time. So in this context, we have two different paradigms to represent systems. One what we call mathematical and the other what we call graphical approach. In mathematical approach, you have seen the differential equations. You know now the state space representation is going to be needed, and oftentimes we would be interested in how the outputs and inputs are correlated and understand the characteristic equations. And similarly, in the graphical approach, we would love to have block diagrams, which are going to give us a visual tool to understand the systems. And similarly, we have a slightly modified graphical approach, what we call signal flow graphs. We may have other approaches as well, but we would probably discuss it later on, just like the bond graph methods. And then we have to have some sort of conversion tools to convert from one paradigm to the other, from differential equations to the state space representation, from here to the transfer functions, from transfer functions to the differential equations. We would love to have certain conversion approaches. And similarly, for the graphical paradigm, we would love to have the approaches to convert block diagrams into signal flow graphs and vice versa. And so on and so forth. We would also love to have certain tools where we can transform from the mathematical paradigms to the graphical and from graphical to the mathematical approaches. And these tools are going to help us out to understand and apply all those tools which are possible to understand these systems better, analyze them better, and improve the performance. So that's why these are going to be very important tools for the control system development. So we will pursue these conversions today, and initially mathematical paradigm will be explored. The first conversion that we will pursue is that from differential equation to transfer function. And for that, I will ask you to recall the nth order differential equation. Now this differential equation is going to involve the derivative terms in it. So that was something like dn by dt raised to power n of the state variable x, which is obviously dependent on time, added with the coefficients multiplied with the lower order derivatives. So this is going to be a n minus 1 d n minus 1 by dt n minus 1 of x. Then you keep on doing it all the way to the second last term is going to be a1 dx by dt, and then you have a naught multiplied with x to be equal to the inputs. Now in our case you may have the differential arrangement for the inputs as well, so that may be written in that form that you have dn minus 1, the highest possible term that may be there, by dt n minus 1 of u, which is also going to be dependent time possibly, and that is going to be added with let me use a different notation for these coefficients. Let it be b n minus 2 to be consistent with the order of the derivative terms. So this is going to be dn minus 2 by dt n minus 2 of u, and then you keep on adding the other terms all the way to the last term, which is going to be b naught u. Now in this particular arrangement, you can see that you have a left hand side which involves the states, and you have the right hand side which involves the input. And also I would ask you to consider or reconsider the zero initial conditions. Why so? Because that was the requirement for the transfer function. We have already seen that, so we will keep this arrangement with zero initial conditions. And that is not going to be problematic because eventually we are going to use the principle of superposition. So whenever you have non-zero initial conditions, that response is going to be added using the superposition with the response coming in from this side. So that is going to be not overly complicating the stuff. So in this continuation, I'll ask you to recall the definition of transfer function. This transfer function was defined in that sense that you have the output over input. Now, X is considered to be output because you will love to have the important states to be considered as outputs. So that is going to be added in it. Now, in this particular scenario, this is going to be equal to an expression where you have some numerator in the S domain divided by denominator in the S domain. Now, considering this ratio of X over U, you will, let me use a different color now for the input side. So this red box is going to be when transformed into the S domain, it is going to be mapped over here in the numerator of the expression. And the one with green, I'm going to have another box in green. This is going to be mapped onto the denominator. And I'll ask you to consider this transformation that all the times we have considered this S domain to be achieved when you have the Laplace transformation taken, and that was something like you have the time domain transformed into frequency domain when you took the Laplace transformation of the expressions. So these Laplace transformations are going to change or alter the time domain expressions, which are differential equations, into algebraic equations that you can very easily manage. So this is going to be, for that reason, this side is time dependent. This is going to be dependent time, and this is going to be dependent on S, which is the complex variable. So let me write that one down. It is the complex variable. Now, with this realization that you have to write down a transfer function in the S domain, you need to take this Laplace transformation of the expression. And since the zero initial conditions are indicated, so this is not going to be overly complicated. So that would be something like if you have in the assumed solution, assumed input to be something like b e raised to power st, which is the assumed input. So that would mean that the solution is going to be of X is going to be, because these are linear systems, of the same type. So this is going to have some change in the amplitude, obviously, but the nature of the signal would remain intact because of the linear system. Now, if you have that kind of arrangement, you can obviously see that you can take the derivative d by dt of this whole expression. So if you do that, that would be x dot, that is equal to, in that particular scenario, s multiplied with a e raised to power st. And if you take another derivative, for example, x double dot, so that is going to be s squared times a e raised to power st. So this gives you kind of a very simple, straightforward set of expressions that the power of s is going to grow bigger, or it is going to be consistent with the order of the derivative term. So for that reason, this transformation, in order to construct the transfer function, is going to be not that difficult. So we will do that. We will continue this discussion on the next slide as well. Now I can write down the transfer function. by inspection, which is going to be a ratio of x of s over u of s. Now, as you can see that it is going to be equal to something appearing in the numerator divided by some expression in the denominator. So the numerator expression is going to be corresponding to u of s, and that is over here. So I'm going to use this expression to write the numerator over here. So that is going to be, for that reason, if I can encapsulate it in green. So this is the expression that I'm interested in to be transformed so that would mean that the very first term in that is this term, which I can write down using the arrangement given over here. I can write down that. So this is going to be equal to s raised to power n minus 1, like the very first term, added with the second term over here, which contains the coefficient bn minus 2. So this is going to be bn minus 2 and s raised to power n minus 2 because of the derivative term in there. And then you can keep on doing it all the way to reaching to the final value, which is going to be just like the p naught expression. Now u of s is taken common from this when you have transformed it from the time domain to the s domain, and that when taken to the other side it comes in the denominator, and that's why we have treated the right hand term in the fashion that we have written down. And similarly, by inspection you can observe what is happening on the left hand side, and that is going to be corresponding to the red box that I'm making now. And I can once again by inspection observe what is going to be the very first term in that. So I can write down the expression corresponding to that. So this is going to be s raised to power n, because the derivative term corresponds to the power n, added. Then you have the coefficient an minus 1 corresponding to the derivative term which has reduced to one order. So this is going to be an minus 1, and then you have s raised to power n minus 1, and you keep on doing it all the way to reaching to the final term over here, which is going to be a naught. And since x of s is going to be taken as common, so when taken on the other side, so it belongs to this red box that I've made over there. So with this realization that you can write down the transfer function by inspection very easily, this is the method of doing that. But for that you have to realize that you are going to make a jump from the time domain to the frequency domain. Let's go through one simple example to illustrate this conversion. Let it be like you have a voltage source which, after passing through this switch, powers up this circuitry which contains one resistance and a very simple circuit of having an inductor in it. So you have R, you have L, and this is the current passing through this circuitry. So in that particular realization, you can very simply and very easily write down the differential equation. There is only one energy storing element, so that's why the order of this differential equation is 1. So that was something like L di by dt plus Ri. Now obviously, because you have the time rate of change of current, you need to have an initial condition. So we are saying that using this switch, you can say that I at 0 is going to be equal to 0. And that is going to be equal to some input given to the system. So let it be like an input u of t given to it. So this is going to be something like you have u of t given over there. Now with this realization that you have a differential equation in your hand, you can very easily transform it using the Laplace transformation into an equation in the S domain. So that is going to be something like the Laplace transformation, which implies that Laplace transformation of dit by dt is going to be equal to, we have Si dependent on S minus this current at t naught. And since this is equal to 0, so this is going to be Si of S. And we have said this earlier that you are going to consider 0 initial conditions, so that is not going to be problematic in that sense. And it also implies that the Laplace transformation of I, for that matter, is going to be equal to I of S, and this would indicate that Laplace transformation of U of t is going to be equal to capital U of S. So with this realization that now you have got these individual elements, you can make use of equation A, and that would be something like A can be rewritten. So on one side you have L multiplied with Si of S plus R I of S to be equal to U of S. Now you can take common over here. So this is going to be Ls plus R on one side, and then you have I of S on the other side. That is equal to U of S. That would mean that you can very simply write down I of S over U of S, which is the transfer function. Obviously, that is equal to 1 over Ls plus R. So this is a very simple, straightforward case in which you started, let me use a red color over here, you started from a differential equation, although it was a very simple differential equation, and you transformed it into a transfer function. And it fulfills that criteria that transfer function is going to be based on Laplace transformation with 0 initial conditions, and it is going to be structured in terms of output over input. So in this case, the output is the current passing through this RL circuitry, and input is the voltage applied to it by the voltage source. So you're going to conduct similar exercises, and you can very easily do by inspection this conversion from differential equation to Laplace transformation. The second conversion that I'm going to attempt is that from state space equation to transfer function. So state space equation is going to be the very first point to start with, and that would make this kind of arrangement that you have x dot to be equal to ax plus bu, and you have an auxiliary equation which is called output equation, that is written down like y to be equal to cx plus du. Now we are going to start from here and expect that after executing the method, we are going to find a transfer function. And for that, we have to start from here, and you can observe that the first term is x dot term. So I can make you recall that for that we have just observed that x dot is equal to dx by dt, and this is going to be equal to, in that sense, the way we have written down, it is going to be s x of s. So that would mean that for any single derivative term, you are going to add s corresponding to that expression. So if I use this realization, this would mean that you can write down this as s x of s on this side to be equal to a with x of s. And by the way, I should also make you recall that these are with the zero initial conditions added with b u of s. So I'll write down with zero initial conditions. And we will use the principle of superposition if there are non-zero initial conditions to add to the transfer functions later on. So with this arrangement that you have written down an expression in the S domain, because that is the necessity to transform into transfer function. So I can see that, all right, that's one good thing to have, but you can see that x of s is appearing on this side, and you can see x of s is appearing on the other side as well. So why not arrange them in a sense that you can take them common? So this is going to be equal to sx of s minus ax of s on this side to be equal to b u of s. So that would mean that you can have the x of s taken common from here, and that is going to be s. So s is written down, but since you have taken the x of s common, so the remaining is going to be an identity matrix, so that the subtraction can be accomplished corresponding to matrix A. So this is going to be the expression corresponding to the left hand side, that is equal to b u of s. Now you can write down this to be identifying x of s expression, that is this thing is going to be taken on the other side. So with this realization, this is going to be si minus a inverse times b u of s. Now if it is required that you write down an expression for x of s over u of s, that is going to be a very simple straightforward expression that you can evaluate this expression si minus a inverse. So this is going to be the transfer function. But oftentimes you would be interested in finding out what is going to be the output corresponding to the input. So that is going to be another step that you can take using the equation over here. So if I take this equation on this side, that would mean that you have, if you take the Laplace transformation, this is going to be y of s to be equal to c x of s plus d u of s. So now you can plug in the value of x of s over here from this expression. So that would mean that you have y of s to be equal to c, and you have si minus a taken inverse of times b u of s plus d u of s. Now you can take u of s common from both the sides. That would mean that you have y of s to be equal to c si minus a inverse b minus d into u of s. And that would mean that you can now write down the other transfer function y of s over u of s, which is going to be equal to c si minus a inverse times b minus d. We'll solve one example to further illustrate the process. This is the state space equation, which obviously represents x dot to be equal to ax plus bu. So you can identify readily that this is the matrix A and this is the matrix B. And the output equation is defined like this, which says y is equal to cx plus du, but in this case d is equal to 0. So with this realization that you have got matrix A, B, C and D which is 0, you can further investigate the equation which was defining y to be equal to C Si minus A inverse multiplied with B plus D. And this is multiplied with U, which obviously can be taken on the other side, which says y over U is going to be equal to C into Si minus A inverse times B, and since D is equal to 0, I need not to write that. So I'm going to use the matrices defined above alongside this equation to further find out the transfer function. So in order to evaluate this expression, I need first of all this expression to be evaluated. So let's first of all find out that is going to be Si minus A. So this is equal to the matrix Si, which is going to be S0, 0, 0, S and 0, 0, 0, S, where S is the complex variable. And minus you have the A matrix that is already written down over here. 0, 1, 0, 0, minus 4 and 3, and minus 1, minus 2, minus 1 and minus 2. So I can readily find out that. So this is going to be equal to a matrix, very simple matrix, which is S minus 1 and 0, 0, S plus 4, then minus 3, and then you have 1, 1, and S plus 2. So this is your Si minus A matrix. So what is going to be Si minus A inverse in that particular scenario? That is going to be adjoint of this matrix over determinant of it. So we can separately find out the two expressions, so that we will do on the next slide. Now first of all we have to find out the adjoint of Si minus A, but before I do that I will write down the Si minus A matrix, which is written down already in the previous step. That is S minus 1, then you had 0, you had 0 and S plus 4 over here, minus 3, 1, 1 and S plus 2. So this was your Si minus A matrix, which means that now you can compute the adjoint of Si minus A, and that was, if you recall, that was a matrix using the cofactors of all the elements. And on top of that, you had to take the transpose of that. So we're going to follow the same route over here in order to compute the adjoint. And the very first item is going to be corresponding to this location. So this cofactor is going to be S plus 4 into S plus 2. Then you have minus sign and then minus 3 multiplied with this element 1. So I'm going to write that one down. So this is going to be S plus 4 into S plus 2, and then you had minus minus plus 3. So this is the first of the elements. And then for the second element, because you have to take the transpose of that, so you will consider this element, and if you consider that, obviously you are going to multiply minus 1 with S plus 2, and then 0 into 1 is going to be 0. So with that realization, you are going to find out the expression for this position. So this is going to be, for that reason, minus minus plus. Then you have s plus 2. Yeah, that is it. And then you have the other element, which is going to be corresponding cofactor of this element. So this is going to be minus 1 into minus 3, then minus 0. And that is going to be placed over here. So with this realization that this is going to become equal to 3, I will write down that. All right, moving on. Now about this location, you have to find the cofactor corresponding to this location. So this is going to be, in that sense, 0 into this minus 3 into 1. So with this realization that this is going to be equal to minus 3, because you have to change the sign once again, and then you have corresponding to this location, which means s into s plus 2 minus 0. So this is going to, for that reason, become s into s plus 2. And then for the last location, you have to change the sign. And then you have obviously 3 into s. Yes. All right, so then moving on, for the last row, you have to consider the last column of si minus a, and that is going to be, for that reason, with a minus sign, s plus 4, if I'm not mistaken. And then you have with a minus sign over here, s plus 1. Yes. And then you have for the last, s into s plus 4. All right, so this is your A joint, and then you are going to use this in conjunction with the determinant to find out the inverse of this matrix. So let's do that on the next slide. Now we can define the determinant of this matrix as well, and that is going to be equal to using this matrix. So this is going to be S multiplied with s plus 4 into s plus 2 minus minus plus 3 into 1. Then you have minus minus plus 0 plus 3, and then you have all the remaining item to be 0 because this is the 0 coefficient. So I can quickly write that one down. There's going to be s into s plus 4 multiplied with s plus 2. Then you have minus minus plus 3. And then you have minus 1, but since it is already, it has to change the sign, so there's going to be plus 1 into 3. Yes. So you are going to write down this expression. When you expand it, it is going to become, so this is going to become s into s square plus 4 plus 2, 6s plus 8 plus 3 plus 3, and I can multiply s with that. So this is going to be s cube plus 6x square s square plus 11s plus 3. So this is going to be determinant of si minus a. Now you can write down the expression corresponding to the inverse of si minus a very easily using this expression and this matrix. And now you can use this full expression because you have taken the inverse of that matrix, si minus a, and then you can have that multiplied with c on one side and b on the other side. So using this expression, I can write down the expression like this, that you have y of s over u of s to be equal to c, which is already over here 1 0 0 0 0 1 multiplied with the big matrix that we have seen already. So this is going to be adjoint of Si minus A that we have computed already, divided by the determinant of Si minus A, which we have already computed. Then you have to multiply B on the other side, which is already written down over here. So this is 0 0 1 0 0 1. And when you multiply all these things together, this is going to be something like this, that you have 1 over determinant of Si minus A, which is already computed, S cube plus 6S square plus 11S plus 3. And then you have this matrix 1 0 0 0 0 1 multiplied with a joint matrix, which is S square plus 6S plus 11. If we multiply the two terms together, this is going to be S plus 2. This was 3, and then you had minus 3 S into S plus 2, and then you had 3S, and this was with a minus sign, S plus 4. You had minus S plus 1, and then you had S into S plus 4 over here. And then you have to multiply the B matrix as well. So I'll find a little place over here so that I can fit that one in. 0 0 1 0 0 1. So when you do that, this turns out to be 1 over S cube plus 6S square plus 11S plus 3. And then you have this full multiplication result into a 2 by 2 matrix, which is going to be S plus 2 over here. You have 3, and then you have minus S plus 1, and then you have S into S plus 4. So what happens in this kind of arrangement, that you are left with this term, and you have this term, and then you have this term, because of the way the non-zero elements of C and B are structured. So you are going to be left with that. So this is going to be Y of S over U of S. As you have already noticed, that this is going to be a 2 input 2 output system, and this is also obvious because your B matrix is indicating that you have one U corresponding to this and another input corresponding to this coefficient, and similarly for the C as well, you have one output required for this and another output for that. So these are the only non-zero elements in C matrix and B matrix respectively. So this would mean that you have a 2 input 2 output system. So with this realization that you are going to have multiple transfer functions, so the very first transfer function is y1 of s over u1 of s. So that is going to be the first term corresponding to this. So this is going to be s plus 2 over s cube plus 6s square plus 11s plus 3. Similarly, you are going to have y1 of s over u2 of s to be written down like this, that you have 3 over s cube plus 6s square plus 11s plus 3. And then you have similarly another expression like y2 of s over u1 of s, and that is going to be, if I use a different color corresponding to this green block, so this turns out to be minus s plus 1 over the same denominator. And similarly, you are going to have y2 of s over u2 of s to be equal to this expression divided by the characteristic equation, and that is going to be s into s plus 4 over the same expression. Now in that particular scenario, you can see that you have 4 transfer functions corresponding to individual outputs and corresponding inputs. So on top of that, you can also identify that the characteristic equation is the denominator and that is when you put this s cubed plus 6s squared plus 11s plus 3 to be equal to 0. And this equation is going to be further elaborated later on when we are going to discuss the stability of the system and the placement of poles on the S-plane, which is one very important tool to identify or comment on the stability and performance of a particular system. So up until now, we've seen how the differential equations are transformed into transfer functions. And we have seen how state space model similarly can be transformed into a transfer function as well. So this is what we have seen already. But what about the state space model to be transformed back to a differential equation? What about that? And this is what we are going to do now. So we're going to start from this arrangement that you have the state space model available. So given this state space model in this form that you have seen so many times, x dot to be equal to ax plus bu, and here you can recall that x were the number of states which are going to be structured in a vector of n by 1 sized, and you have the inputs to be, let it be like r inputs, so you have r by 1 sized vector for that, which means that you have a which is going to be n by n, and yet then you have the input matrix b to be equal to n by r. So given you have this arrangement of the state space model available to you, you wish to transform it into a differential equation. And this is the problem that you need to determine the nth order differential equation. And specifically for a particular input in terms of, in most of these cases, you define a particular input. So in terms of, let it be the ith state. Now in order to do that, what I can assume that we can take the Laplace transformation of the state space model. So this is what we're going to do now, that take this equation, which is equation A. Let me use a different notation so that you are not confused with, let it be equation number 1. So 1 can be transformed into another equation using Laplace transformation. So this would mean that you can have s x to be equal to ax plus bu. Now in that case, you have seen this thing already, that when we're going to take this a to the other side, so that you can take the x common, and that's the beauty of Laplace transformation, that it transforms the equation, the differential equation, into an algebraic equation that you can kind of easily manipulate. So for that reason, it is going to be s I minus a, and then obviously you can take the x common from there, to be equal to b times u. Now, in this particular case, if I can define, let me use a different color. If I define this thing to be a matrix M, and you have X already defined to be equal to, let it be this whole thing defined as another matrix Z. So that would be something like you have Mx to be equal to Z. And this is what you have already seen uh, while discussing the matrices already, and you were using in that particular scenario a rule which was called uh, Kramer's rule, which may be applied to solve this system, which was generally when you have the n equations for n unknowns. So this is what we are going to try to explore, this Kramer's rule. And let's continue this on the next slide. Now, for such systems, the Kramer's rule is quite simple. It says that you can find out the ith x to be equal to determinant of mi over determinant of m. So this m is quite clear, but what this mi is, this mi is actually matrix M, but with a little modification, which is modified in this fashion with the ith column replaced by vector z. Now you already know this z is placed already over here. So what you need to do is to use this vector z and place it in the matrix M at a specific column location, and that is going to be for that corresponding input a modified matrix Mi. So this ratio is needed to be defined or found out, and that is going to define how the differential equation is structured. So in this particular case, just for the sake of clarity, I would write one thing already, where matrix M is obviously Si minus A matrix. So we're going to use one simple system to construct this transformation. So we'll do one example to understand that. So we can have the matrix A defined for this case to be, let it be 0, 0 and minus 3. Let it be like that. And then you have 1, 0 and minus 3 over here. Let it be like 0, 1 and minus 1. And let it be like you have B matrix defined, the input matrix to be like 1, 0, 0. So there is only one input in this case. That would mean that the Z can be defined to be U, 0 and 0. Since you know that Z is equal to B times U. Now with this realization that you have a matrix A, you need to construct another matrix, which is Si minus A matrix, and that can very easily be found out. That is going to be S, this is going to be minus 1, this is 0, and then you have 0, and then you have S over here, and you have minus 1 over here, and then you can change the signs for 3 and 3, and this is going to be S plus 1. So this is your Si minus A matrix. Now, once you have found out that, that is obviously equal to M. So you know what this M is, and you know what the vector x's, obviously, because this is 3 by 3, so you're going to have 3x, x1, x2, and x3. And then you can see already that you have found out Z matrix as well. So from here, we can say that I can find the determinant of matrix M, and that is going to be determinant of this whole matrix that I've written down over here. So this is going to be placed over there, and that is, when executed, is going to be S into S multiplied with S plus 1, and then you have minus plus 1 into 3, and then you have minus plus 1 into 0 into S plus 1, and minus 3. So this is going to be 1 into 3. So with this realization that you have got this arrangement, this is can be rewritten like this, that you have S square plus S plus 3 over here, plus 3, and that is equal to S cube plus S square plus 3S plus 3. Now the next question would be how to find out this determinant of M1. Now since you know that this is the subscript 1 over here, that would mean that I'm going to modify this matrix M on the first column right over here, if I may indicate that. The rest of the matrix would remain intact, and that is minus 1, S and 3 over here. You have 0, minus 1, and S plus 1 over here. And that first column is going to be your vector Z plugged in over here. That is U, 0, and 0. Now you can take the determinant of this, and that would be equal to when you have U multiplied with S into S plus 1, and then you have plus 1 into 3, and then you have plus 1, and that actually comes out to be 0. So this would mean that you have this is to be equal to S square plus S plus 3, and then you have to multiply U with that. So this is your determinant of M1. Now you can use the Cramer's rule, which says that the x1 in this particular case would be equal to determinant of M1 over determinant of M, and that is equal to, when you plug in these values, this would be this would indicate that you have S square plus S plus 3 into U over this S cube plus S square plus 3S plus 3. And that, you can see, looks similar to a transfer function. The only difference is that you have U placed over there. But I can use the same formulation to construct the differential equation as well. So let's do that. So I can write down this expression to be like this, that you have x1 with S cube plus S square plus 3S plus 3 on one side, and then you have S square plus S plus 3 into U on the other side. And then obviously you can rewrite that. That is going to be S cube x1 plus S square x1 plus 3S into x1 plus 3x1 on one side, and then you have on the other side S square U plus S into U plus 3 into U. And since you know that you have once taken the Laplace transformation, you have transformed the differential equation into an algebraic equation. You can now take the inverse Laplace transform now, and by inspection, because you can register that for transfer function you have assumed the zero initial conditions as well, so you can now rewrite that as well, and that is going to be equal to d cube x1, and now x is in smaller case, over dt cube plus d square x1 over dt squared plus 3 dx1 by dt plus 3x1 to be equal to, now you have d square u of dt over dt squared plus du by dt plus 3u on this side. So this is your differential equation. Required, in this case it is the third order differential equation. But what if you're interested in not x1 but x2? What if that? Is the variable of interest. So in that case, you can obviously recall that that would be, in that particular scenario, the Cramer's rule is going to be like x2 to be equal to determinant of m2 over determinant of m. So in that particular case, m2 is going to be the matrix where the second column is going to be replaced with z vector. So you would do that, and similarly for x3 as well. Now, in order to make a conversion from transfer function back to differential equation, if you observe what we have done in the previous example, we have already done so. If you observe the Cramer's rule application, what we have done is like we have defined this expression which can be rewritten in terms of a transfer function. So that would be x1 of s over u of s if you take the u on this side, and that is going to be equal to s square plus s plus 3 over this s cube plus s square plus 3s plus 3. And this is exactly the transfer function that we have discussed already so many times. So in order to make a conversion from this back to differential equation, what you need to do is to take the inverse Laplace transform that we have already accomplished in the previous example, and that is going to give you this differential equation as a result of that. So this conversion has been done already by inspection. Now, in that sense, we have explored all the possibilities in the mathematical paradigm. But we still have to see how these mathematical expressions can be converted into graphical representation, and how the graphical representation schemes can be converted from one form to the other. But that what we are going to cover in the next part of this lecture. So we will stop here for a moment, and for the remaining part of this discussion, you can see part 3 of this lecture.